Hey there. Today we're going to talk electricity and more specifically electrostatics. A lot of you all have a bunch of conceptions already coming in from, years of schooling and talking about electricity in some form or fashion. So I asked you on Socrative just to enter a whole bunch of words that come to mind whenever you start thinking about electricity. And here's what we got from you. A lot about currents, circuits, light, negative, positive, all that kind of good stuff. So let's talk about what exactly it means to have a charge. Charge, kind of like mass, is not an object itself, right? I can have a cylinder that has a mass of 2 kilograms, and mass is just a property of it. Sometimes you'll hear the definition, it's the amount of matter, but that's kind of hand-wavy. Mass is just mass. It's just a thing we have, and it's how we interact with gravitational fields. Similarly, charge is just a property of protons and electrons, and it's how we interact with electric fields. So the property of charge is measured in this new unit of coulombs. Again, in the fall semester, everything could be broken down into kilograms, meters, seconds, and not so much now. Coulombs is a whole new idea since it's just a base unit of a property of matter. And all it really is an excess or a deficiency of electrons. Again, if you think about an atom, you've got those protons and neutrons all densely piled into the nucleus of the atom, and the electrons are zipping around in a cloud on the outside. So the electrons are what are transferred between objects and shared. So if I gain a whole bunch of electrons, I'm going to get negatively charged. All right, cool. If I lose a whole bunch of electrons, then I'm going to get positively charged. That means I've got more protons left over than I have electrons, yielding a net positive charge. Speaking of protons and electrons, they each have the elementary charge, just opposite signs. That elementary charge is a constant that you're not necessarily going to need to memorize. I'll provide it for you on a test or anything like that, but it is 1.60 times 10 to the negative 19th coulombs, known as the elementary charge. So that means electrons have negative 1.6 times 10 to the negative 19 coulombs. Protons have positive 1.6 times 10 to the negative 19 coulombs. A lot of times you'll see this just denoted as the little letter E. So if I say I've got a charge of negative 3e, all that means is that I've picked up 3 electrons. I have 3 electrons more than I have protons. Again, they have the same charge, but they've got different masses. Protons are a lot bigger, a lot more massive than electrons. So if they experience the same force, the electron will move a lot more easily, but they've got the same charge. Meanwhile, neutrons have no charge and are neutral. A few rules about charges. All charges quantized. Here's what quantized means. It's basically kind of like a step ladder. I can be on step 1 or I can be on step 2, but I'm not going to be on step 1.5. Or train platforms. I can be on platform 9 or platform 10, but I'm not going to make it to platform 9 3/4 unless I'm a wizard. Also, unless you're a wizard, you're not going to find any charge other than an integer multiple of the elementary charge. So I could have 1 times 1.6 times 10 to the negative 19. Or I could have 2 times 1.6 times 10 to the negative 19, or 3 times that number, or negative 2 times that number if I've picked up electrons. So all these are totally valid, except I'm never going to encounter something like 1.5 times 1.6 times 10 to the negative 19. That's impossible. I'm not going to lose a half of an electron. On top of this, charges are also conserved. What that means is that I'm never going to gain or lose charge without gaining or losing electrons. And it's not just going to pop out of nowhere. So if I've got a closed system, once again I rope off a certain number of objects, and let's say I've got one object with a charge of plus 2e, another object with a charge of minus 2e, so right now I'm at net 0, and another object of negative 3e. So now I'm at net negative 3 times the elementary charge. all together, all these objects together. And then I let them bounce around a bit. They come into contact, they trade electrons back and forth. However it shakes out, I'm going to end up with an object with a total of -3e within this system, as long as nothing else has come in to add or remove electrons. So if I leave them in contact long enough, then they'll each end up with the same charge. They're going to try their best to reach equilibrium. So in that case, I would just have -1e, -1e, and -1e among all of them. They will just spread it evenly out if they come in contact long enough. But the total charge will always be the same. A lot of times this is called the law of conservation of charge. Now, a lot of this was figured out by a very clever gentleman named Charles Augustin de Coulomb. Clever enough to even have the unit of charge named after him. Fancy. He was French, if you couldn't guess, and he studied torque on metal wires. He actually ended up figuring out the force between two objects with charge, just like most scientific discoveries, kind of by accident. Now, objects with charge also follow Newton's laws, the first, second, and third law. So anytime, if I'm charged and I feel a force because of another object with charge, I know I'm being pulled with the same force that I am pulling on it, with attraction or repulsion. Those forces are always going to be the same. And here it is. The force equals K times Q1 times Q2 all over R squared, where K is what's known as Coulomb's constant and is 9 times 10 to the 9th Newton meters squared per Coulomb squared. It's really, really, really similar to universal gravitation. The main difference, well, there are two of them. One, electricity is way stronger than gravity, like absurdly stronger. We're going to do some examples later that really highlight that. And two, gravity can only attract, while electrostatics, I can get an attraction or a repulsion. And that's a very, very key difference. There's no such thing as really a negative mass, while there is such thing as a negative charge. So, if I am solving problems with Coulomb's law, here's how I go into it. A lot of the confusion can come around actually that negative. So, I like to ignore the sign to begin with. Right? I know from elementary school that like charges repel and opposite charges attract. So I can figure out the direction. Force, just like it was all fall semester, is a vector, and all that the negative means is direction. So ignore the sign for now, because you can figure out the direction for yourself, and enter just the absolute values of Q. You'll use Coulomb's law, that equation that was just given, to figure out the value of the force in newtons, and then figure out the direction for yourself. It always helps to draw a picture. If you come across multiple objects with charges, and you need to find the net force on, let's say, one of them, here's the best way to do that. Just like every other problem we've done that involves force, start by finding each force individually. And then you'll use some vector addition. So, let's say I've got 3 objects. I'll call them Q1, Q2, and Q3, just because I'm that fancy. We'll say Q1 and Q2 are positively charged. They're forming sort of a triangle, Q1 off to the left, Q2 up above, and Q3 on the right. And I want to find the net charge on Q1. Well, first I'll find the force that it's feeling. Sorry, not the net charge, the net force. I want to find the net force on Q1. Well, first I'll find the force that it's feeling due to Q2 only. Now, if I label the distance from Q1 to Q2 as RA, and the distance from Q1 to Q3 as RB, then I'll find the net force, or the force just from Q2, as KQ1 Q2 over RA squared. Okay? Since it's a repulsive force, I know that it points directly away from Q2. Then I'll do it all over again between Q1 and Q3. And that force will just be KQ1 Q3 over RB squared. Now, because Q3 is negative and Q1 is positive, that force will be pointing directly toward Q3 because it's an attractive force. All right. Once I have that, if I want to find the net force on Q1, all I got to do at this point is break each individual force by itself into its x and y components. So I'd have to know something about an angle or something like that. Once that's done, just like every other vector addition, add up all your x's, add up all your y's, smack the Pythagorean theorem down on it, and you've got it. So I'll just simply ignore all the rest of the charges and treat it like a free body diagram problem. Add up all the x's, add up all the y's, Pythagorean theorem, and I'll find the net force acting on it. It should probably be mentioned that I don't care about what the value of the force is between Q2 and Q3 if I'm looking at the net force on Q1. That doesn't affect it. Also, Q1 does not exert an electric force on itself. So that's important to note too. The triboelectric series designates what materials are more likely to give up an electron versus what materials are more likely to take an electron. So if I rub two types of materials together, let's say polyethylene, that's a type of plastic that a lot of plastic bags are made out of, and let's say steel. I've got a steel pipe and I rub it on a rubber bag. Because steel is further up the positive end of the spectrum on this chart, then steel is more likely to give away an electron to the polyethylene, which is farther down on the negative side of the chart. But if I, for example, rub my steel rod against, let's say, a lead sheet for some reason or other, steel is farther on the negative side, so it's more likely going to become negatively charged and take those electrons, whereas lead will be more likely to give up those electrons. So that's how you can read this chart and figure out what's more likely to become positively charged and what's more likely to become negatively charged. Grounding is the phenomenon of connecting some sort of an object to the ground. The electrical symbol of it just kind of looks like a wire coming down, and then it's connected to three parallel horizontal lines, each one as you go down getting smaller. Basically what you're doing is you're connecting it to an infinite reserve of electrons. Now, there's not really an infinite number of electrons on the Earth, but it's close enough, especially if you're looking at just a standard-sized object. When an object is grounded, electrons can freely flow into the Earth, out of the Earth, and back and forth as they want to. Again, they have a natural tendency to try to reach equilibrium, so a lot of times grounding is used to discharge a charged object. If I've got too many electrons and I give it a path to the ground where it can freely spread out, heck yes, all those electrons hate each other, they're going to take that path. Similarly, if I'm positively charged and I connect to the ground, then all of these electrons in the ground see a positive party going on up there, and they're like, yeah, and they start to pile on until I get neutrally charged. But it can also be used to charge a neutral object. We'll actually talk about that a little bit later. And finally, conductors and insulators. You all probably already know a little bit about them. Conductors conduct electricity. They allow electrons to freely move about within them. Insulators do not. But there's a bunch of common misconceptions. For example, a lot of people think that insulators cannot be charged, and that is not true. They can be neutral or charged just like conductors. Now there's a different mechanism by which they get charged. Conductors get charged via processes called conduction and induction. We'll talk about both of those later. Insulators get charged just by rubbing two materials together. Conductors allow charges to move freely, like I said, and they distribute evenly over the surface. Versus insulators, which do not allow them to move freely, so once an insulator is charged, all that excess charge stays at the point of contact of the insulator. And finally, another phenomenon you need to understand is called polarization. Now, if I bring a charged object near an uncharged object, it will get polarized. If it's a conductor with the electrons free to move about, all the electrons will head to one side or the other. Well, not all the electrons, but a large component of electrons will move from one side to the other, leaving behind a positive charge on the other side. So polarization is just a separation of charge. Insulators are, the electrons are not free to move around, so they will get what I like to call atomically polarized. Electrons are still free to move about their individual atoms. So it's a much smaller scale polarization, but it still happens. And we'll look at some examples of that in class as well. But until then, have a great time, and I will see you all later.